Binary search is one of the basics of computer programming, and so we're going to practice it and kind of explore how binary search is used, like what is it, and you really want to get good at it, honestly speaking, because it's going to come up in coding interviews. Actually, you do use it in everyday life. Some of these algorithms that we teach in these classes, oftentimes, like they're not used in real life, so it kind of feels like it's a waste of time, but for binary search, it actually does get used. Alright, so what is binary search? Well, let's kind of talk about the idea of searching first. Alright, here I have some numbers, alright, so I've got some numbers, and they're not in order. So it's like numbers 1 through 10, but they're not in any particular order. Alright, so we got 5, 10, 4, 1, 3. Alright, so let's say we had a number that we wanted to search for, right? So like, let's say we didn't actually like know all the numbers in the list. We can go through them one by one, and then once we find the number we're looking for, then we can say, hey, the number's there. Or if we don't find the number we're looking for, we could, throw an exception or maybe get back a -1 and say, hey, too bad, so sad, did not find the corresponding number. All right, so let's say our target number that we're looking for, all right, is, let's say it's 9. All right, so we're looking for 9 in this list of numbers. Now, we're going to, if you're doing this programming wise, like picture a for loop. So you're going to go through the numbers one by one by one and ask yourself, well, hey, is this number 9? So we go to 5. Is this a 9? Nope. 10? Nope. 4? Nope. 1? Nope. 3? 9. There we go. All right. So once we find the number we're looking for, right, then we've hit the number. We've searched. This is called linear search. All right. So what we're doing right now is linear search. Linear search, all right? And what does that basically mean? Linear search is where essentially if I were to give you a list of data, you would loop through the data one by one until you found the thing that you were actually looking for. So why is this not so great? Well, because as this list of numbers right now is not very big, but picture if we had like 1,000,000 numbers, right? Like 1,000,000 numbers. And so what's the worst case scenario in that case? So, for example, we found 9 pretty early on, right? Like, we didn't have to go through the whole list until we found 9. We got to 9 and it stopped. But, like, what if we were looking for a different number? Like, what if we were looking for... Let me kind of get this out the way here. There we go. What if we were looking for a different number? Like, let's say a number that didn't exist in here, like 11. Okay, 11 isn't in this list, but let's say, for example, we were looking for it. Well, we'd have to go through the entire list before we could say for a fact that we did not find 11. So that means that we had to go through all 10 digits before we could say, okay, 11 doesn't exist in this list. Well, picture if we had 1,000,000 numbers, okay? So instead of having 10 digits like you see here, we've got 1,000,000 of them, all right? Which means in order to, worst case scenario, in order to search for something, we have to go through every single number in the list until we reach the end, meaning we have to go through like 1,000,000 different digits. That would suck, all right? So linear search is basically just go it one by one, and linear search has a big O, O of n, all right? And you're like, what the heck is that? Basically, big O kind of tells us how well algorithms scale. It doesn't necessarily mean how fast they are. It's more about, hey, if I throw a bunch of data at you, how well are you going to be able to handle it? If you've ever been to like a restaurant, then you kind of already know this concept. So if you go to a restaurant and there's only like 2 or 3 people there, well, they get their food out pretty quick, right? You sit down, the waiter doesn't have much to do, the cook doesn't have much to do, you get your food, that's it, very, very quick. But if you go to a restaurant when it's extremely busy, where there's like a line out the door, then the cook has a bunch to do, the waiters have a bunch to do. The restaurant doesn't scale very well. Some restaurants scale really well where they can get slammed, but they don't care. You're going to get your food out just pretty fast, and you'll have great service. Some restaurants scale poorly, meaning that if they get slammed, they get slammed, right? Like, you're not going to get a really good experience eating there. So, since that's the case, we have linear search, and linear search is kind of like a restaurant that doesn't, it can't handle, like, a huge crowd coming all in at once. All right, now, let's get to the main topic, binary search. All right, so let me move some of this stuff out the way. And that's linear search. We don't need to talk about that for the moment. All right, so here on the bottom, I have everything sorted, and that's kind of important because sorting the list actually allows us to use binary search. And so what's binary search? Well, let's go back to our original idea, and let's say we were looking for the number 9. Okay, cool. Well, since this is sorted, what I'm going to do is I'm going to basically say, okay, I'm going to look at the middle number. All right, so I've got a bunch of numbers, and there's like I'm going to be like a number that's straight in the middle. Okay, so this has got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we'll say 6 is in the middle. Okay, so here we go. Here's my middle number. Well, we're looking for 9, right? Is 9 going to be on the left side of 6? Like, think about, I'm splitting this in half now, right? Like, picture it's like a line down the middle, just like this. So we have some numbers on the left, we have some numbers on the right. Okay, so we have 1 through 5 onto the left of 6, and 7 through 10 to the right of 6. All right, is 6 9? No, 6 is not 9. It's not equal. All right, cool. Is there any reason to search in this area? Like, is there any reason for us to even look at these numbers? Because we know for a fact that 9 is greater than 6, and because 9 is greater than 6, anything to the left of 6 is not going to be what we're looking for by definition, because this list is sorted. And this is the key point of how binary search works. This is very important we get this concept. All right, there's no point in looking to the left of 6 because 9 is going to be to the right of it. Okay, no matter what happens, we know all the numbers to the right of 6 are going to be bigger, right? If 9 is bigger, that's where it's going to be. So we can actually just basically skip searching through like certain parts. Let me kind of undo here. All right, so basically what you can think about is that we're kind of just like, cross all these out. All right, cool. Well, now we have this list left over, 6 through 10. All right, cool. Let's get the middle one. So I'm going to get rid of this thing here, and we're going to have a new middle. Oops, I'm going to get rid of all of them. There we go. And then we have this new middle. All right, so here we go. And let's take the middle number, which will be 8. All right, so we're going to do this. We're going to do this again. So now we're going to ask ourselves, okay, cool. Is 8 equal to 9? No, 8 is not equal to 9. All right, 8 is not, okay, but so we didn't find 9 yet, but where should 9 be? Same idea here, right? 9 is greater than 8, so there's no reason for us to loop through anything to the left of 8. It doesn't make any sense. So we're going to cross these out. Goodbye. And then we're going to go ahead and take the middle, and we're going to change it again. All right, and this time the middle is going to be 9. Well, we found it. Cool. Okay, so compare the two. Let's say, for example, I wanted to do 9 up here, right? I had to go through 1, 2, 3, 4, 5, 6, and I was finally able to get 9. But with the list sorted, I had to have the list once, okay, got rid of, I didn't have to, like these 5 things here, I did not have to loop through them, right? I just ignored them. And then I halved it again, and then I cut out 2 things here because I didn't have to loop through them, and I got to 9. I got to 9 in 3 steps, and basically, like, did not have to, like, do anything, right? So I did, like, 6, took out the half, 8, took out the half, and then got to 9, and then bam, there I was, all right? So clearly, I iterated or looped through a lot fewer numbers using binary search than I did for the linear search. So this would be an example of binary search. Okay, and because we're sort of having the space, like basically every time I'm searching for the number, I'm having the amount of things I have to iterate through. Okay, this is going to be a big O. It's going to be logarithmic. Okay, log of n, which is going to scale way better, okay, than O of n. All right, if you look at the graph, like I'm going to actually let you do this on your own, a little bit of homework for you. Graph both of these. Look at the logarithm, like the logarithmic function, and then the linear function. Put them on a graph and look at the first quadrant, and you'll see that this scales way better. All right, so now with binary search, I basically cut out a lot of work I know I don't need to do because the list is sorted. Now, that's the big thing about binary search is that the list needs to be sorted. Okay, it's not going to work right with this unsorted list. So sometimes it is actually going to be worth for you to take the list and sort it and then perform binary search. Okay, so now I think we have an idea of what binary search means. All right, so hopefully you get the idea. Next, we're going to kind of code up the basic algorithm in Python, and this is one of those rare times I would actually tell you to like memorize this. I actually wrote the algorithm for binary search like about a dozen times before I like seared it into my brain, and it's really worth doing that because it's such a fundamental thing that they're going to expect you to know on coding interviews. Again, you do actually use this out in the wild. Even if you don't really realize you're using binary search, you're using it, so it is actually quite important. So it's one of those things where I would actually commit to memory. Okay, let's actually implement binary search. I'm going to use Python. You can obviously write binary search in whatever programming language you are most comfortable in, so make adjustments as necessary. But what we're going to do is I got my test cases below, and I've also got a array here so we can help visualize it. All right, so first off, what we're going to do is we've got two inputs to this function. I've got the array I'm going to search through and the number I'm trying to find. I'm going to make an assumption that the array that's coming into this function is sorted. Okay, remember binary search relies on a pre-sorted array. So we're not going to, our function is not going to do the sorting for us. It has to come to us in a sorted fashion or else it won't work. All right, I'm going to have two variables, start and end. In Python, you can actually declare multiple variables on the same line when you separate them by a comma. And so the first thing you write will be the value for the first variable, and the second thing you write will be the value for the second variable. So the start is going to be 0, because with binary search, when we first start off, the first index is going to be 0. This is index 0. And then the last index is going to be like the last thing here. So it's going to be the length of the array minus 1. Okay, so what we're saying is our first search space is going to be at the beginning to all the way to the end. That will change as the algorithm does its thing. All right, but then we're going to have a while loop. While start is less than or equal to end. A while loop makes the most sense here. All right, the reason being is that we don't know how many times we're going to cut this array in half. So basically a while loop is great for do this thing until I tell you to stop. I don't know how many times you need to do it, but just do it till I tell you to stop. All right, now we need to find this middle number, this middle index. All right, so I've got the numbers 1 through 9 here. Again, this is up here just to help you visualize how this works. Remember, this function works for any sorted array. Okay, any numbers, it could be a billion numbers. All right, could be. I'm just using this as an example. All right, so we've got this middle point. Well, how do we find it? Well, we could take the total number of elements, the length of this array, and divide it by 2. So we could look at the start and end. All right, so what we could do is the midpoint is equal to start plus end divided by 2. And so this may look weird in Python. Remember, sometimes if we divide by 2, we might get a fraction, right? We may not necessarily cleanly divide by 2, so this will do the rounding for us. Now, this is what you'll see in most binary search. Like when you look up the algorithm, you'll probably see this. What I like to do, however, is I like to do start plus end minus start divided by 2. And the reason I do that is mostly habit, but it also prevents an overflow error. Now in Python, that's not a big deal. Python integers can be arbitrarily large. It does, the programming language doesn't care. But if you're working with Java or like C++, you cannot have arbitrarily large numbers. So what will happen is if you do it the regular way, so I'll put the regular mid. If I put that here, and I do start plus end divided by 2, what will happen is, what happens if this if the end is like really big? Like let's say it's like, I don't know, 20 billion. Okay, so some huge number. Well, you'll have an overflow error. But with the second way, what will happen is even if you start off with a really big number, you're subtracting. So you will always end up with something smaller. That way you will always try to like stay within bounds. So that way that this won't have an overflow error. For Python, it doesn't really matter. But for other languages, I think actually for Java, the Java built-in binary search that came with the Java language for 10 years had that bug in it. And then eventually someone had an overflow error and they had to change Java and fix that. So it's not a small thing. All right, so now we need to basically ask ourselves, okay, we've got the middle point, and need to ask ourselves, is this our target number? Let's say we're looking for 7. Okay, let's say the target number were 7. So if it were 7, it wouldn't be equal, but we need to check to see if it's equal, because if it's equal, then we found our number. So we'll say if the mid is, the number at mid is equal to target, okay? Array. All right, cool. So hey, check the index in the middle. Is that our number? If it is, we can just return the index where we found it. Else if the array at mid is less than the target. All right, so again, let's take our example with 7. The middle number is 5, but the number we're looking for is 7. 5 is less than 7, then what do we do? All right, since 5 is less than 7, we therefore know everything to the left is useless. All right, it doesn't matter. There's no reason for us to look at it. So what we're going to do is we're going to take the start, which used to be at index 0, and move it all the way up to 1 above 5, right? Because we know 5 isn't the number we're looking for, and all these are garbage. So take the start and move it all the way up to 6. So we're going to change the start and move it all the way up to the middle point plus 1. Now for the opposite, let's say we're looking for 3. 5 is greater than 3, so we know that 5 and everything over to the right of 5 would be useless. All right, so if the number we're looking for is less than, then what we're going to do is we're going to take the end, which used to be at 9, and move it all the way over to 4. So we're going to do end equals mid minus 1. All right, if we get out of the while loop, then what that means is we never found the number. So let's say we're looking for 12, right? 12 isn't even in this array. So we would get through the whole loop. We would basically iterate through the entire array till we got through every single number, and we would not have found 12. In which case, we're just going to return -1, which basically means, hey, I didn't find the number. All right, let's test it. So I've got some test cases down here. One where the number is in the array, one where it's not. So let's go ahead and do Python binary search. Cool. The target here is 3. And 3 is at index 0, 1, 2. Found it. 12 doesn't exist in this array, and so we gave back -1. Now, I don't tell people to memorize stuff too often, but I would memorize this algorithm. Like I literally put it on note cards when I was studying this, so that I could like sear it into my brain. Because pretty much you're not going to do too much change to the code. So like if a problem requires binary search to like solve it, you're not really going to be changing this algorithm too much. So it's really good to have it committed to memory so you're not stumbling over it. So what I did was I just actually wrote it out like 5 or 6 times before my brain like was like, this is how it's supposed to go. So again, I don't tell people to memorize things too often, but this is something I would memorize. Now, this is the basics of binary search. The idea from here is to look at problems where they're binary search problems, but they don't necessarily appear that way at first glance. So binary search is really useful for doing things other than just like looking for a number in an array of numbers. You actually can use it for things like finding the square root of a number, which we're going to talk about next. If you're enjoying this course, please come to codingyourcareer.com, where we have courses on back-end and front-end technologies that are hot in the market as we speak. We've got courses on C#, Java, SQL, and any other thing that you might need to level up your coding career. We are even currently offering a live class in API development. So if you'd like to sharpen your skills in .NET and C#, we have a live class where you'll be working with a senior developer in learning all about different backend technologies and how to level up your coding career. So again, please visit codingyourcareer.com. All right, let's continue with our binary search madness. Now, binary search obviously is great for searching for things, but actually you can use the algorithm for a lot of other things that you might not necessarily think like binary search would be used for. And one of them actually is, a classic example is finding the square root of a number. Now, I know what you're thinking, Jonathan, like most languages have some kind of square root function. Okay, Java has, math.sqrt, and JavaScript does, and et cetera, right? And if it doesn't come built in with a square root function, you can go get a library. But like, if you wanted to like have your own square root function, you know what I'm saying, you could build one. And you could build one that's pretty efficient. But let's see how we could try to like solve this without using a built-in library or the built-in functionality that comes with like some sort of math library. All right, let's say I have a target number 16. Okay, I want to find out the square root of 16. And then, yeah, I know you can do that in your head, but let's have the computer do it this time. One way you could do this is I could basically like line up all the numbers, okay, starting at 1, and take the square root of the, square the number, and then see if it equals my target number. All right, so we start at 1. Okay, 1 squared is 1. Is that 16? Nope. All right, cool. Go to 2. What's 2 squared? 4. All right, oops, let me get the little pen. All right, so 2 squared would be 4. All right, and that's not 16. 3 squared would be 9. 4 squared would be 16. Bam, we found it. All right, and that would work, right? So this would be a way in which we could find the square root of a number. Just take all the integers, right, that in a row, and then just start at 1, square them, and see if it equals a target number. If it doesn't, move on to the next one. The problem with this is that it's not very efficient. What I mean by that is Well, the problem is, like, 16, 4 occurs pretty early on in the list. But what if we were doing like the square root of, like, I don't know, 25,610 or something? I'm just throwing out a number. But right, like some really big number. Well, that would mean that you would have to, like, you can picture the number of numbers we'd have to, like, iterate through would grow linearly, okay, based on how big the number we're searching for is. Right? So, like, right now we have 12 numbers, but, in the future we might need, like, 13, 14, 15, etc. And that could grow really big. So, if we did our algorithm where we just went one by one and squared the numbers and matched them to our target, this would be a linear algorithm, right? It'd be O of n, which basically means it wouldn't scale that well. So, remember back to our restaurant example, okay? So, O of n, linear, okay? Like a straight line. And so what that means is, again, back to a restaurant example, you have a restaurant, and some restaurants, they deal with having a large amount of customers really well. They're well stocked, they're well prepared, the cooks and the chefs and the waiters are all well trained. So if they get a bunch of people all at once, the restaurant's able to handle it, you get your orders out, you get your food. Some restaurants, they can't handle a large amount of customers coming in at once, and things begin to break down, they get slower, and the more and more people that come in, the more problems there are. Okay, so some restaurants can scale better than other restaurants. I think that's a kind of a cool way to think about it. All right, so how can we do this with, like, where does binary search come in, John? That we're not really searching for something. Actually, we are. We are searching for something. We're searching basically for what is the square root of this number. Okay, that's really what this problem is all about. So one of the things you can do when trying to figure out whether or not a problem could be solved with binary search is don't just look for, like, they're not going to just, like, lay out binary search for you, like, on a silver platter. A lot of times, if you're thinking to yourself, like, man, I'm kind of like linear, I'm going for, like, a linear, like do the brute force first, where you're just, like, kind of like linearly going through each number, and then ask yourself, okay, cool, I'm really just searching for a number. Right, if you're searching for a number, you could try to reformulate what you're asking yourself so that binary search would work. I'm just kind of going through number by number here, like 1, 2, 3, 4, 5, 6, till I hit the square root of this number. But really, what I'm just basically saying is, like, go up through the numbers until you hit the target number. Well, we know binary search makes that way more efficient. So once you see that pattern kind of pop up, that's your brain's way of saying, like, hey, I should probably do binary search, and then that would actually make this a lot more efficient. So how does binary search work with this then, Jonathan? All right, remember, the core algorithm doesn't change. All right, we're still going to find the middle number. Let me use green this time. All right, we're going to go find the middle number. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. We'll just say this is the middle number, 7. Okay, cool. So we'll find 7 squared. What's 7 squared? 7 squared is 49. Okay, cool. Is that now? It's like, okay, Jonathan, that's great. Okay, cool. Is this number bigger or smaller than our target 16? Okay, that's really what we're going to ask ourselves. Well, I'll put our target here, 16. All right, is this bigger or smaller than 16? So ask yourself, if 49 is bigger than 16, then obviously 8 squared is going to be bigger than 16, and 9 squared is going to be bigger than 16, and 10 squared is going to be way bigger than 16. So is there any reason for us to even care about any of these numbers to the right? Because we know for a fact all of them are going to be bigger than 16. So none of these are going to be the square root of 16. So bye-bye. Don't need to care about you. I do not need to iterate through you. Go away. Okay, cool. So since we got that, so we saved ourselves some work. Oops. We saved ourselves a little bit of work. We said, my eraser tool doesn't want to work with me today. All right, we'll just leave that. And then, okay, cool. Those are all gone. All right, great. Now, we have half the numbers left over, so we're going to get our new half, which is going to be 4. So I'll put it here, 4. Okay, great. Now, it just so happens that once we square 4, we've hit it. Okay, we got 16. Awesome. But you see how we, like, saved a bunch of work? I, like, literally just basically crossed off a bunch of work and found my number quicker in fewer steps than I would with all up here. And again, this is a small example. We're doing like 16, so like in the linear search, you only have to go through 4 numbers. But even then, you can see I didn't have to go through as many steps. I did half, and then I found it. So here, let me actually do another number where we have to do a little bit more halving, and then maybe it will be a little clearer. So let me go back a bit. All right, let's say we're looking for 144. Okay, so let's do 144. What's the square root of 144? Okay, again, binary search, start in the middle. Okay, 7 squared is 49. All right, is 49 less than 144 or greater than? Okay, so since 144 is bigger, we therefore know that 6 squared is not going to be 144, and 5 squared is not going to be 144, because if we didn't reach it with 7, we're definitely not going to reach it with any of these smaller numbers. So all of these, bye-bye now. Okay, don't need them. Bye-bye. All right, cool. Now our new set of numbers is 7 through 12. Great. So let's go through that. Now I'll go to the middle one. Let's go 10. All right, and 10 squared is 100. So we still ask ourselves the question, all right, is 100 less than or equal to 144? 100 is less than 144. Therefore, 7, 8, and 9 will never get us this number, because if we didn't get there with 10, we're certainly not going to get there with 7, 8, and 9. Bye-bye now. All right, cool. Go to 11. Now you see what's happening. 11, all right? And then we can do 11 squared, and let's do 11 squared. Okay, 121. All right, that's less than 144, so therefore it's 2 over here, so we get rid of this. And then we basically say, okay, cool, we get rid of this, and we get rid of this, and then we got 12. 12 squared is 144, so therefore we found it. We found our magic number, 12. See how it's still fewer steps? If we look at the linear one, right? So I have this again. I have the amount here. Then I have it again. Then I have it again. It's like 3 steps, and then we get to like 12. Here, I have to, with the linear way of doing things, starting at 1, squaring the number and see if it matches 144, I would have to go through every single number all the way to the end. All right, so you could see that the binary search algorithm, even though we're not like, it's not the normal way you're used to seeing it, we're still searching for a number, all right? And so therefore, this is still going to be way more efficient than doing it linearly. All right, let's code this up in Python. All right, and let's take a look and see how it works. Alright, so to go over the code for the square root problem, I actually brought over the code we just did for binary search because I wanted to kind of showcase the fact that we're following the same basic, idea, alright? So, the template doesn't really change. Alright, so instead of, looking for a number in an array, we are looking for the square root of a given number, alright? So, for example, 25, alright? So we're going to look for 25. So we're not going to get an array to iterate through, so really what we're going to do is we're going to go through all the numbers from 0 up until n. Alright, so that's the first change we're going to make. We also can kind of say, if n equals 0 or n equals 1, then we're just going to return n. That's an edge case, so, we're also assuming they're going to give us positive integers. Alright, we're not going to deal with, imaginary numbers or anything like that. Okay, so we still have the start and end. We still have a while loop. We still do the mid, except this time we're going to change this around. So if mid times mid, all right, is equal to n, all right, that's going to be the first kind of change. And then otherwise, it's pretty much the same, right? We're just going to do mid times mid is less than n, and then keep the else. All right, so now you'll kind of notice that we really didn't do much to this section of the code, right? I just said instead of looking for a number, we're squaring the number. So if we take the number that we're currently looking at, the number in the middle, and square it, and it is equal to n, then we found our number. If not, then we can continue on. And also at the very end, we're not going to return -1 because we're not. That was because we wanted -1 to indicate that we didn't find the number. In this case, we're going to return end. This I'll show you why in a moment, but essentially, we have to also deal with not perfect squares, right? So 8, for example. And so I want to make certain that we round. Okay, we get close enough to where it's supposed to be. And that we can handle those cases. Most of the time, we can just look at the perfect squares, though. Okay, so let's try this out. So as you can see, I didn't really change anything, right? This part changed. I changed the if statements a bit, but the same basic logic of here's a group of values, get the middle one, check to see if is it on the right, is it on the left. That did not change. So let's go ahead and try this out. I'll do Python square root. Okay, we get 5. If I try, I don't know, square root of 144, we get 12. All right, and so now if we do something that's not a perfect square, like 8, okay, you'll get 2. right? Which will get, close to it, but not quite it. All right, so that's why we were going to do the code for finding the square root. Again, as long as you know the binary search template, if you know the binary search algorithm, then making the modifications to it for this code is actually quite trivial. All right, and that's why I was saying this, memorizing this is actually worth it, because it will make solving binary search problems so much easier. All right, as is tradition, we're going to go over another problem that does not look like binary search, but totally is. All right, so this is called Koko Eating Bananas. I don't really know where they come up with that stuff for these word problems. That always bothers me, because when I was a kid, I would do word problems. It would be like, Billy brings 50 bags of candy to school. And I'm like, why the heck is Billy bringing 50 bags of candy to school? How did they even let him in the building with that? And then I derail, and I don't even think about the problem anymore. Don't do that with this. This is about a monkey eating bananas, and so we've got an array of numbers, and each index represents a pile of bananas. So here we have 3 bananas in the first pile, and the second pile we have 6 bananas, 7 bananas, 11 bananas. And what we want to do is the monkey wants to eat the bananas such that he eats all the bananas in every single pile before time runs out. So he has 8 hours to eat the bananas, okay? If it takes him 9 hours or 10 hours, he's out of luck. I gotta eat all the bananas within 8 hours. Neat. All right. Now, the key thing about this problem that tripped me up a long time ago, and I want to make sure I go over this, is that the monkey cannot eat one pile and half of another pile at the same time. So the monkey can work on one pile of bananas per hour. Okay, that's just the constraint. All right. So for example, if the monkey ate 4 bananas per hour, he has to eat all the bananas in the first pile first. He can't just eat the first pile and a little bit of the second pile. He eats the first pile, even if he could eat more, right? Even if there's some leftover capacity to eat bananas, doesn't matter. You have to eat the first pile in an hour and then move on to the next. That's kind of the key thing that tripped me up when I first encountered this problem, right? So I want to make that clear. All right. So how could we? And the idea of this problem is I want to figure out, right, what's the least amount of bananas I can eat per hour and still hit this target? All right, so essentially I want to be able to figure out, okay, cool, what's the fewest amount of bananas I can eat per hour and still be at 8 or under? Because, otherwise this problem would be easy, right? You would just be like, okay, cool, the biggest pile of bananas is 11, and so that means I can eat everything in one shot. I eat 3 in an hour, 6 in an hour, 7 in an hour, do 4 hours, and we'd be done. But that's not the least amount of bananas I could eat per hour and still maintain the time limit. All right, so what we could do is there's 2 ways to go about this. We'll go over the brute force approach first, and then we'll talk about binary search. Okay, the brute force approach is essentially just start off at 1 and then figure out whether or not you can eat the bananas in that amount of time. If you can't, move on, increment the number up and try it again. I think it's pretty clear that 1 is not going to work, right? So if the monkey eats 1 banana per hour, it will take him 3 hours to get through the first pile and 6 hours to get through the second pile, and already we're over 8, right? So we've already gone over our time limit. So 1 is not going to work. So we know that 1 and not going to work. Let's try 2. All right, if we eat 2 bananas per hour, it will take us 2 hours to eat the first pile. Remember, we don't get to chew into the second pile. We have to finish a pile and then move on. So the first hour he eats 2 bananas with 1 left over. Then the second hour he eats the last banana and finishes the pile. So we have 2 hours here, and then 6 divided by 2 would be 3. 3 hours to do this one. And then basically we're going to divide by the number and round up. So this would be rounds up to 4. So we can basically it's 3 with remainder 1, right? So we need that 4 hours. And already we're over. Okay, 2 plus 3 is 5. 9, that's over. So that won't work. So 2 bananas per hour is too slow. We can't eat 2 bananas per hour while still being under 8 hours. Let's try 3. Okay, 3, we can do 1 hour for the first pile, 2 hours for the second pile, 3 hours for the third pile. Not looking so bad, and 4 hours here, and we're over. Okay, so this is too slow. All right, let's do 4 bananas per hour. All right, so we can still do this in 1. We'll still do this in 2. We'll do this in 2. Okay, and then we'll do this in 3. 3 plus 2 is 5, 7, 8. Bam, we did it. All right, now, what's the efficiency of this algorithm? This algorithm is actually going to be pretty slow because if you think about it, we're kind of starting off from 1 and going up to 4, right? We're going up linearly. All right, so that's n. All right, and for each one of these, we're going through pretty much every single pile, right? To figure out what, like, you know, like how many hours it takes to go through each pile. So for each one of these numbers here, right, we have to figure out, we have to go through each one of the things inside the array and figure out how many hours it takes to eat that pile. So in the worst case scenario, right, so here we hit 4 pretty early on, which is nice, but in the worst case scenario, we would check everything from 1 all the way up to 11, all right? So we would check everything from 1 up to 11. So essentially, we're kind of checking n, and then we're multiplying that times the whatever the maximum is. So the maximum of this pile of bananas, all right? So the big O of our brute force algorithm is O times n. It's O of n times maximum, the maximum of this pile, which in this case is 11. All right. This is not very good. And again, this is a small amount of bananas. There's not that many of them. We hit 4 pretty early, so it may not seem to you like this is really saving that much time. But if you look at if it were binary, right? If we're doing the binary search, we know that's log of n. At the very least. Maybe it's a little bit bigger, maybe it's a little bit smaller. It's going to be logarithmic. That's going to beat any kind of linear algorithm out of the water, right? So in that case, how do we identify like this is a case where binary search would work? And the way you kind of can see that is, first off, you saw me like I was starting to do like things linearly, right? It was like 1, 2, 3, 4. And so we're basically taking each number, right, and we're doing some sort of computation with it repeatedly. Take a number, do some computation with it repeatedly. Take a number, do some computation with it repeatedly. And we're comparing it to something. Okay, so we have this comparison over here with h. Remember what square roots, right? With the brute force with square roots was, take this number, do some computation with it, compare it to a number. Take this number, do some computation with it, compare it to a number. This is no different. Take the 2, do some computation, compare it to a number. Take the 3, do some computation, compare it to a number. And so if the problem kind of gets into that flow, then we could use binary search. All right, so let's kind of rework this a little bit, and then we will see how binary search works and makes it a lot faster. Okay, so I've reworked some things. All right, and so now let's picture that the monkey is going to eat bananas per hour in intervals from 1 to 11. Why 11? Well, that's the biggest pile. Okay, so the biggest pile in this array is 11. So, and the least amount of bananas the monkey will eat per hour is 1. So it's going to be some number between 1 and 11. Okay, cool. We'll use binary search. Cool. Pick a number, do a calculation. Well, we'll do 6. 6 is in the middle. All right. So we'll picture how many hours does it take to go through this and eat all 6. Okay, so we can basically just go through, make a little side table. All right, and then just divide and take the ceiling. So we can eat the first pile in an hour. We can eat the second pile in an hour. And then we can eat the third pile in 2 hours. And then we can eat this the fourth pile in also 2 hours. All right, so cool. So we got 4, 5, 6. All right, so h is equal to 6. Not bad. Okay, not bad at all. Can we do better? All right, so let me clear a little bit of this up. I'm still going to keep these over here for clarity's sake. Okay, so we know, therefore, that if this hits h, can we have a lower, like basically can we have one of these numbers, the lower numbers, hit it? Because if we think about it, like maybe some of these numbers to the right will give us an h of 8 or less, but they won't be less than 6, right? We're trying to find the minimum number of bananas to eat per hour. So even if one of the 7 or above, even if some of these numbers were to give us an h that's valid, 6 is going to be less. 6 is valid, and 6 is less than all of them. So there's no reason to calculate 7, 8, 9, 10, or 11. All right, so I'm going to repeat that logic. Okay, we calculated what the H would be. Okay, how many hours the monkey could eat the piles of bananas for eating 6 bananas at a time. 6 is valid. All right, this is a valid, like 6 works. If you eat 6 bananas per hour, you can eat through all the bananas and still get 8 or under. But we don't know if there's a smaller number of bananas per hour that the monkey could eat and still maintain and still be under H. But we know that anything to the right of 6 is not going to satisfy that, right? Maybe 7 or 8 is valid. Like maybe they give us an H of 8 or below, but they're bigger than 6, so there's no reason to do them. We're looking for the minimum number. So everything to the right is that we don't care about. All right. So cool. Awesome. So what do we do next? We look at 3. All right. Let's look at 3. Cool. We eat the first pile in an hour. We eat the second pile in 2 hours. We eat the third pile in 3 hours. And then 4 hours for the last one. 4, 7, 9. Oops, we're over. Okay, cool, we're over. All right, so this is too much. All right, so therefore now we have this bound. So now we don't have to look at 1 and 2, right? 1 and 2, there's no point in doing a calculation for 1 and 2. There just is no point. Why? Because we know if 3 went over, then 2 and 1 are also going to go over. So all we got to do is look at 4 and 5. Okay, cool. So we can do the algorithm again. All right, we can do the 4 this time, and then we already did 4 basically in the previous one, so you know that it works. But you see how we just didn't, like, all these numbers, in the other way we did this, we had to do a lot of extra work. We did 1 and 2, we would have to also do 7, 8, 9, 10, 11 in the worst case scenario, but instead we just cross all this work out. We just don't care. Because we know, like, once you do the calculation for one number, right, that you know, based on that calculation, whether or not you should bother with the other numbers. And that's why binary search makes this way more efficient. So now, this is logarithmic, and it's going to scale way better, and we're going to do way fewer computations, okay, in order to figure out the number. And again, it's hard to, like, really appreciate that when usually in problems they don't give you, like, these, they're not going to give you an array of 1,000,000 numbers for you to work with, right? But like when you really scale this up and you can see the difference between how many computations you make, it really makes a big difference. All right, so hopefully you've gained a new appreciation for binary search and all the magical, wonderful things it can do. I would highly recommend to go to the Python section and type that code out like 5 or 6 times until it sears itself into your brain. All right, binary search is a fundamental algorithm that you just have to know. It will come up on some interviews depending on what company you're going for, and it does come up in real life sometimes. So being able to understand this does stretch out your brain muscles too, so it is well worth your time in studying this. And hopefully I was able to clear some stuff up and you understand binary search more than when you started this video. All right, now for the banana problem, this is going to be a little bit different than the template that we normally did for binary search, although honestly speaking, not too much difference. We still can basically kind of bring this over. All right, so I really want to bring the point home that this template for binary search, like when you memorize it, it really makes this a lot easier, because even though this problem we're going to be making like more changes to it than like what you would normally do, it still is basically the same general structure. All right, so we have the banana problem that takes in an array of piles, and then the hour, like basically the time limit we have to eat all the bananas. All right, so we're still gonna have a start and an end, except this time we're gonna start off at 1 because the monkey isn't going to eat 0 bananas. And then we basically want to check all the way up to the highest number in the array. So let's say we have 3, 6, 7, 11. So down here I have some test data. So what we're gonna do is we're gonna do max of piles. All right, so that's what we're going to do, max of piles. So basically 1 banana per hour up until the pile with the most bananas, because you're not going to eat more than this, because we're looking for the minimum number of bananas to eat per hour. So it would never be more than this, because like this would be eating all this huge pile in 1 hour. Okay, but still, again, see how we're doing a start and end? Like we're starting off with that. Now, instead of doing start is less than or equal to end, we'll just do start is less than end. Like we're gonna end the loop. We're gonna end the binary search when start and end are equal to each other. All right, we still find the midpoint. That didn't change. All right, and now the if statement, like this part will be the part that's a little more different than what we normally do. Okay, so we're gonna have a variable called time to eat, and we're gonna set that to be 0. And we're gonna loop through all the piles. So we're gonna do for pile in piles. And we're going to check, okay, cool. So we're going to eat the pile. How do we figure out how many hours it takes to eat the pile? Well, you take the pile and then you basically divide it by like how many bananas you're eating per hour. So what we can do is we could actually say time to eat plus equals math.ceiling. Okay, so I'm using the math library in Python. However, in your language of choice, however you round up. So again, you want to be able to round up. That's what we're looking for here. So we're going to take the pile and divide it by the number of bananas we're eating per hour. All right, so it's important we round up. So for example, let's say we were eating like 4 bananas per hour. Well, then the first pile we eat in 1 hour. And then the second pile, 4 doesn't go cleanly into 6. So we want to round up to 2. Okay, because it takes 2 hours to eat the pile of 6 bananas if you're eating 4 bananas per hour. All right, and so we're just going to go through each one and then say, okay, cool, how much time does it take to eat each pile, and sum all that up. Then we say, okay, cool. If the time to eat all the bananas in all the piles is greater than our time limit, well, that's not going to work, right? We have to be able to eat all the bananas within the time limit. If we go over the time limit, then we're done for. But if we went over the time limit, then basically what that means is any number to the left of this number, right, any number smaller than the current number of bananas we're eating per hour is not going to work. If this number didn't work, if this number was too small to eat all the bananas in the allotted time, then anything less than that number will also be too small. So we're going to take the start, the left side, and we're going to make it mid plus 1. All right, so we're going to bring all it over. Okay, in this case, there's only really one other option, because here's the thing. The other option is, oh, okay, we did actually eat as many bananas as we need in an hour, but could we also do it with less time? All right, so we actually did find, okay, cool, we found a number of bananas to eat per hour where it actually did meet the criteria, but could we find a smaller one? In which case we'll say the n is equal to mid, all right, because we know that we're not going to do anything to the right of it. So if we found the bananas per hour, right, that met the time limit, any number that would be lower than it would be something we would want to look at. Any number bigger than it on the right is something we're just going to ignore. All right, and then at the very end, we're going to return start. Okay, so basically the number to the left, because that's going to be the smaller one. All right, so we're going to basically start with 1 up to the maximum of the pile, so the biggest number in the pile, which in this case is 11. We will continue this loop so long as start does not equal end. All right, the second that the 2 meet, that is when we stop the algorithm. We get the midpoint just the same way we did. We have a time to eat, which will start off at 0. We'll loop through every pile, 3, 6, 7, 11. And we will divide this number by whatever the mid number was. And we'll round up. So that way, in case we have 4 bananas per hour and we have 6 bananas in the pile, it will take us 2 hours to eat it. Then we'll compare. We'll take the total time to eat all the bananas to our time limit. Okay, if it's over our time limit, we therefore know that it's we need to eat more bananas per hour. So all the things to the left of that number are irrelevant. They're not going to work if this number didn't work. Otherwise, we're going to try to see if we can find a smaller number. Like this number worked, but hey, let's go and look at some other smaller numbers and see if they work. After we eat through all the array, we should be able to find the number of bananas per hour that would be the smallest. All right, so let's go ahead and give this a shot. Call this Koko Banana, and oops, let's see what I do. Oh, it's not ceiling, it's math.seal. There we go. I should have known from the coloration. All right, we get 4. If we eat 4 bananas per hour, we can stay within the time limit, and that's the least amount of bananas we need to eat in order to eat through all the different piles of bananas. Again, even though this one had a bit of a departure from the standard template, knowing the standard template still helps you kind of fill everything in. One of the things you have to do with problems is you want to reduce what's called cognitive load. the more your brain has to think, the harder it is for you to get to your goal. So give your brain less things to think about. So if it's like, okay, this is a binary search problem, then if it has a template in mind, then it's like, okay, cool, I've got this template. That's one thing your brain doesn't have to think about. So more energy can be spent on, other parts of the problem. That's just a little tip I have for learning in general. All right, so that was the banana problem.